500 million miles from the sun, we enter the neighborhood of the giants, great planets moving in a celestial deep freeze about a distant sun whose light and heat barely reaches them. Giant planets are among the most exciting things that we can see in the sky. You remember that the solar system is composed of a diverse number of objects moving in fairly regular progression about a central star, the sun. In this little model, which incidentally does not attempt to show the size scale at all, we can see the 5 small planets, 4 of them close to the sun, the notable exception, Pluto, very distant from the sun. There are an unknown number of smaller objects in the solar system, the asteroids, meteors, and comets, and the 4 giant planets, which we are going to talk about today. Now, this little model doesn't attempt to show any size scale or distance scale. If that were the case, the sun here would have to be at least 10 times the diameter of Jupiter. Here we can see that size scale a little better represented. First of all, here is just a segment of the sun, that controlling star, which contains far more than 99% of all the matter in the solar system. Here are the small planets as we go outward from the sun: Mercury, Venus, the Earth, Mars, and the exception, Pluto, most distant from the sun. Here are the giants: Jupiter, Saturn, Uranus, and Neptune. And it is Jupiter, the 5th planet from the sun and the first of the giant planets, that we are going to talk about today. Jupiter moves around the sun in an elliptical orbit. Now, the orbits of all the planets as they go about the sun are not circles, but ellipses. This is a rather exaggerated ellipse, but it gives us the idea. That means, as these planets go about the sun, that at times they are much closer to the sun than they are at other times. Jupiter, for example, when it is at the point in its orbit nearest the sun, the point which astronomy calls the perihelion, it is 460 million miles from the sun. When it reaches the other point in its orbit, its aphelion point, it is 507 million miles from the sun. Its mean distance, which is the halfway point between these 2 extremes, and which is the distance that we always use when we speak of Jupiter, is 488 million miles. At this distance, Jupiter receives only about 1/27th of the light and heat that we get from the sun. Jupiter is big. It is the biggest of all the planets and has a mass, that is the amount of material in it, which is more than twice the mass of all the other planets put together. Jupiter's equatorial diameter is 89,000 miles. In spite of this tremendous size, however, Jupiter rotates extremely rapidly upon its orbit. It makes a complete turn in 9 hours and 55 minutes. Which, given an alternation of light and dark for whatever it may be worth at Jupiter's distance from the sun, of less than 5 hours. A night, for example, scarcely long enough to really start sleeping. Jupiter has a very deep and very dense and very fluid atmosphere. And Jupiter's very rapid rotation upon its axis has a strange effect upon its form. I told you that Jupiter's equatorial diameter was 89,000 miles. Its polar diameter, however, is only 82,000 miles. And this is what happens. Now here is a little flexible model of a sphere. You see, its shape can be changed. Now as Jupiter spins so rapidly upon its axis, this is what happens. Watch. You see that rapid spin has moved most of Jupiter's dense atmosphere into a belt around its equator and made its polar diameter much shorter. In other words, Jupiter is what we call oblate. It is an oblate spheroid. Now that means something shaped like a sphere, but flat at the poles. This is the case with all of the giant planets, and even with some of the smaller ones. The Earth, for example, has a polar diameter which is smaller than its equatorial diameter. Jupiter moves about the Sun at a velocity of about 8 miles a second and takes 11 years and 10 months to make its journey about the Sun. That is Jupiter's year. Now, the Earth moves about the Sun in 1 year, Jupiter in almost 12, so that we go about the Sun much more rapidly than does Jupiter. And that, too, causes something very strange to take place. In this model, we can see the Sun and the Earth and Jupiter. The Earth in an orbit much closer to the Sun, Jupiter much farther out, and, of course, traveling much more slowly than the Earth travels. Now, as we watch Jupiter through the year, we see something very strange happen. But first, let's see what really does happen. Now, we can see, as the Earth goes around inside of Jupiter, they both move in a regular, steady pace through the skies from west to east as we see them in the sky. However, notice that the Earth overtakes and passes Jupiter. It actually does this at intervals of about 13 months. When that happens, what we see is vastly different from what really takes place. Now notice, in this little outer sphere here, this is what we see when we pass Jupiter. We're coming up, we overtake Jupiter, and Jupiter stops, goes backward for a little while, and then resumes its normal eastward course. This is due entirely to the fact that the Earth moves in an orbit nearer to the Sun and more rapidly than Jupiter. You've had the same thing happen to you on an express train. You've been riding in the express train, there has been a local on the next track. You overtake and pass that local train, and perhaps you have looked out of the window and seen that, and the local train has apparently been going backwards. This is called retrograde motion. It is purely an apparent motion. It does not really exist. Jupiter knows nothing whatever about it and has been always continuing its normal eastward journey around the Sun. Jupiter's tremendous mass, that is, the vast amount of material it contains, gives it sufficient gravitational authority to hold upon its surface a very deep and very dense and very complex atmosphere, an atmosphere that is made up of some rather undesirable elements. In Jupiter's atmosphere, we can recognize hydrogen, helium, methane, and ammonia. I'm sure all of you are familiar with ammonia. Methane, too, is something very common, for that is what comes out of your gas stove when you turn the tap on. Hydrogen is the most abundant element in the universe. Helium is what they call an inert gas. It doesn't catch fire, but it is extremely light, and we use it on Earth a great deal, particularly in our lighter-than-air balloons. There is an imaginary conception of what the surface of Jupiter might look like. Of course, we have no idea of what it really is like, but this does show the tremendously dense, cloudy atmosphere. Here is a model of Jupiter, which shows its cloud-streaked atmosphere. Now, what is underneath there, we do not know. There are several ideas. One of them is that Jupiter is made up of a dense, rocky core with a diameter of about 37,000 miles. Overlying that rocky core is a layer of ice 17,000 miles deep. And over that, of course, Jupiter's dense atmosphere, about 7,000 miles in depth. The other conception is that Jupiter does not have any rocky core at all, but is simply a sphere of hydrogen. Now, at the temperatures of about 150 below zero, which constantly are on Jupiter, and at the tremendous pressures in the interior of the planet, this hydrogen would be compressed almost to the solidity of metal inside there. As we see Jupiter in the sky, it is always far brighter than any of the stars around it. Here is a photograph of Jupiter taken through the telescope. And here we can see the cloudy bands in that dense atmosphere, lying almost parallel to Jupiter's equator, combed out in that way by Jupiter's tremendous rotational speed. The symmetry of these cloud bands is marred occasionally by spots which appear in the atmosphere of Jupiter. This is a very famous spot. It's the Great Red Spot, which was first seen a little less than 100 years ago and has been there ever since with varying degrees of intensity. This spot is about 30,000 miles long and about 8,000 miles from top to bottom. It would take 3 Earths, if they were placed up there, to adequately cover this spot. Jupiter has 12 satellites, rather more than its share. Now, the Earth has only 1, our moon. Jupiter has 12. 4 of them are big, each of them far bigger than our moon, and 2 of these even bigger than the planet Mercury. These 4 were discovered at one fell swoop by Galileo, the first man ever to look at the sky, or indeed at anything else, through a telescope. The other 8, far smaller and far more distant from Jupiter than are these 4, have been picked up from time to time by other astronomers through the years. One modern astronomer, Dr. Seth Nicholson, has got a score which equals Galileo's. He has discovered 4 of these satellites of Jupiter's, but it took Dr. Nicholson a good many years, whereas Galileo found his all in one night. The 4 outermost satellites of Jupiter, tiny things 15 to 20 miles in diameter and millions of miles away from the planet, are moving around Jupiter in a direction contrary to that assumed by most of the planets. They are going in what we call east to west. This is, again, an example of retrograde motion, but this time the motion is real. We do not know why these planets are moving that way. It may be that they are asteroids, tiny minor planets captured by Jupiter's gravitational forces from the belt of asteroids which moves through about the sun close to Jupiter. The 4 major satellites of Jupiter have had a very important part to play in astronomy, for they were instrumental in the discovery of the velocity of light. Before the 17th century, light was assumed to travel instantaneously. In that century, a Danish astronomer, Olaus Rømer, was timing the appearance of the satellites about Jupiter, the moments when they vanished behind the planet as they went around. Now, Rømer noticed through the year that the interval between disappearances increased, which it should not do because they were running on a fairly regular schedule. And finally, Rømer figured it out. When the Earth is here in relation to the sun, and Jupiter here, as it might be, let us say, in June, the satellites were running on time. In December, when the Earth got around to this side of the sun, whereas Jupiter had only moved a short distance in its orbit, the satellites vanished behind Jupiter 16 minutes later. Rømer reasoned that this was because the light from the satellites had to travel an additional distance equal to the diameter of the Earth's orbit about the sun, about 186 million miles. Now, if you take 16 minutes and divide it into 186 million miles, you come up with a figure which is very, very close to what we accept as the velocity of light today. That is 186,000 miles a second. The next of the giant planets out from the sun, and the one second in size only to Jupiter, is Saturn. And if you ever get a chance to look at Saturn, even through a small telescope, don't pass it up. You'll see one of the most thrilling sights you ever saw. Saturn is the planet with the rings. Saturn is a giant. Second only to Jupiter in size, it has an equatorial diameter of about 75,000 miles, a polar diameter of 68,000 miles. It, too, is oblate, you see, and for the same reason that Jupiter is, because it spins very rapidly upon its axis. Saturn's day is 10 hours and 2 minutes long. Saturn travels about the sun at a velocity of about 6 miles a second. You see how that rule holds now? The nearer the planets are from the sun, the more rapidly they travel. The farther we get, the slower they go. Jupiter, 8 miles a second, Saturn, 6 miles a second. And it takes Saturn 29.5 years to make its journey about the sun. Saturn's atmosphere is very much like that of Jupiter, composed, we believe, of very much the same unpleasant substances, with a difference only due to the fact that Saturn is considerably colder than Jupiter. Saturn is about 200 below zero all the time. It must have very much the same interior construction as has Jupiter. Here, for example, are comparative charts of what Saturn and Jupiter might look like if we were able to saw them in half. Here is Jupiter with a fairly large rocky core, a very deep layer of ice, and a layer of atmosphere overall. Saturn, similarly, has a much smaller core, less ice, and rather more atmosphere. Saturn is very light for that reason. Indeed, it may be that Saturn, as may be the case with Jupiter, has no rocky core at all, but is a sphere of gas only. However, Saturn is so light that if we were able to find an ocean big enough, Saturn would float in it. Saturn has 9 satellites, which move about Saturn very much as the Jupiter satellites move about Jupiter, practically in the plane of Saturn's orbit. One of these satellites, the 6th one out from Saturn, is named Titan, and may very well be the largest satellite in the whole solar system. It is much bigger than Mercury and is the only satellite we know of which has an atmosphere, although this atmosphere is probably just frozen pools of methane lying in hollows upon the surface of the planet. The 9th satellite from Saturn, the most distant, is Phoebe. And Phoebe is going around Saturn in a direction opposite to that which is taken by the other satellites. Phoebe is a little retrograde satellite and may be a captured asteroid, as were the 4 outer satellites of Jupiter. The most beautiful thing about Saturn, and the most amazing thing, and a thing which is unique as far as we know among heavenly bodies, is, of course, its ring system. Here is a picture of Saturn and its rings taken through one of the great astronomical telescopes. The ring system measures 171,000 miles in diameter, although its depth, that is, its distance from top to bottom, is only about 10 miles. The inner edge of the ring is about 7,000 miles from the surface of Saturn. And the ring itself, the ring system, is in 3 concentric rings. The inner one, which is very faint and very difficult to see, is called the crepe ring. It has the appearance of that dress material that's called crepe. The center ring is the widest and the brightest. Then outside the center ring there is a gap, a space in which there is nothing. And outside of that, a much fainter outermost ring. Now, these rings are made, we believe, of tiny particles, literally billions of them, moving around Saturn with all the authority that a single satellite might have. We do not know precisely the origin of these particles, but they are thought to be the debris from what was once a 10th satellite of Saturn, which came in some manner which we do not understand, too close to the great bulk of Saturn itself, and was torn to pieces by the force of Saturn's gravitational field. That will happen. We know that. If 2 bodies of equal density but unequal mass get too close to each other in space, the smaller of the 2, instead of being pulled solid into the bigger one, will be ripped apart, torn to pieces by the gravitational pull of the larger body. This could happen, and these tiny particles form themselves into this beautiful ring which moves about Saturn now. Saturn is a marvelous sight, even in a small telescope. You see the great golden globe of the planet. Then you see the dark black of empty space between the planet and the inner edge of its rings, and then the golden halo of the ring around it, several shades lighter in tone than the planet itself. One great astronomer has said that Saturn is one of the truly beautiful things in nature. Now, Saturn is the last of the planets that can be seen without a telescope, the last one known to prehistoric man, the last visible planet. Beyond it, of course, are two other giants. And the first of these giants is Uranus, beyond Saturn. Now, Uranus, of course, is not visible to us under ordinary circumstances. It was the first of the discovered planets. Uranus moves about the sun, of course, in an elliptical orbit, very much as the others do, but at a distance which is almost 1 billion miles beyond Saturn, 1,700,000,000 miles. Now, we know that most of the planets have their polar axes inclined to the plane of their orbits about the sun. The Earth is one of them. Our poles are tilted away from the vertical, so that at one time when we go about the sun, the relationship is this. This would be in the wintertime. We actually are nearer the sun then. Then, as a half a year goes by, because the axis does not change, you see, the direct rays of the sun fall upon the equator. That is in the spring. In the summer, the northern end of the Earth is getting the benefit of the sun. In the fall, the reverse of spring is true, and the direct rays are falling on the equator, and in the winter, we are back to where we start. Now, Uranus has this same trouble, except that Uranus overdoes it a bit. The axis of Uranus is tipped over so far that Uranus is literally upside down. Its poles are pointing directly at the sun. So that as Uranus goes around the sun, at one point in its orbit, its one pole, we can't say whether we call it north or south, is pointing toward the sun. At the first quarter of its orbit around, Jupiter's equator is facing the sun. The next stage, opposite to where we were in the first place, another pole. The other pole is pointing toward the sun. And in the final stage of the cycle, again, the equator points toward the sun. Uranus is another planet with an extremely rapid period of rotation. It spins upon its axis in 10 hours and 45 minutes. Uranus, as I said before, cannot be seen without a telescope. It is the first in a celestial photograph, is not very photogenic. Here it is, a slightly fuzzy greenish disk. Uranus was discovered by one of the immortals of astronomy, Sir William Herschel. Herschel, in 1781, was engaged in making a massive survey of the skies with a telescope that he had built himself. He picked up this strange disc-like object in his telescope one night. A few nights later, he had confirmed the nature of his discovery by the motion of Uranus through the skies. Herschel desired very much to name his newfound planet Georgium Sidus, which is Latin for George's star. Herschel wanted to honor, in doing that, his king, George III. However, the name Georgium Sidus for a little while was called Herschel after its discovery. Now it bears the name of Uranus, which is more in keeping with the names of the other planets. Uranus, in mythology, was the ruler, the overlord of all the heavens. Uranus has 5 satellites. They are all going around in what to Uranus is a normal fashion, that is, in the same direction as Uranus rotates. But because Uranus is tipped over so far and is practically standing on its head, these satellites are all technically retrograde in motion. This is a sort of a guilt by association. Uranus had been going around its orbit for a period of about 50 years after its discovery, when it was found by careful, meticulous observation that Uranus was not following as it should the path which was laid out for it, the path which it should have followed when all the known factors affecting its motion were taken into consideration. It was wandering a little bit, deviating from that path. Now, these wanderings in astronomy are called perturbations. And the perturbations in the orbit of Uranus led to the suspicion that there was another body beyond Uranus, farther from the sun, that might be affecting Uranus. 2 young men, one an Englishman, John Couch Adams, and the other a Frenchman, Urbain J.J. Leverrier, set out to find out what this object could have been that was disturbing the orbit of Uranus. They were working independently. Neither one knew that the other was engaged on the same job. And of course, this involves a mathematical problem of the utmost difficulty. Adams, the Englishman, worked on it for 4 years and came up with what he thought might be the answer. That is, the place in the sky where such an object, if it existed, would be found. He sent his figures to the British astronomical authorities And they weren't particularly interested. They took a few looks, cursory glances, and found nothing. Leverrier, at about the same time, this was in 1841, took his figures to Johann Galle, a very good German astronomer. Galle was not only good, but he had an excellent chart of the skies, he had a fine new telescope, and he had wonderful weather. He looked, and on the very night he got Leverrier's figures, he found Neptune, the 8th planet out from the sun, the last of the giant planets. Neptune is big. It has a diameter, an equatorial diameter of 27,000 miles. It is an oblate spheroid, too, like the others. It has 5 satellites. Pardon me, Neptune has 2 satellites. One of them, Triton, may be even bigger than Saturn's Titan, and hence the biggest satellite in the solar system. The other one, near it, is a small one. We don't know very much about them because they are very difficult to see and very small. We must assume that Neptune, because of its size, its tremendous size, has the same kind of an unpleasant atmosphere that afflicts the other giant planets. And it is probably very much the same sort of a thing in its construction. Neptune has a day, that is, it spins upon its axis, in about 15 of our hours. It takes Neptune 165 weary years to make one journey about the sun. To sum the whole thing up, and these are the 4 giant planets that we have been talking about today. Now let's consolidate what we have learned about these planets so far. We find that they are very much alike in that they have slow periods of revolution, long years. They have very rapid periods of rotation, short days. They are at incredible distances from the sun. They have large diameters, and in all but one case, they seem to have a surplus of satellites, and their temperatures are almost unbelievably low. These are the sullen giants of the solar system. They are dreadful places, but fortunately at such tremendous distances that as far as man's present efforts to reach them is concerned, they are beyond temptation.
This is National Educational Television.